In Bose-Einstein condensate, Bose refers to boson. What exactly is a boson?
So physicists are always dividing things up into categories. And one way we divide up all particles, atoms, either into the pile which we call fermions or piles which we call bosons. And any little particle you've ever heard of, an electron, a proton, a photon, they always fall into one pile or another. Atoms are in that category also. And bosons mean that the atoms that behave like bosons, it sort of has to do with how fast they're spinning. They all they're sort of friendly, gregarious. They all like to hang out in the same place. And of course, that's sort of what's going on with Bose-Einstein condensation, is the atoms all being in the same place at the same time. Fermions are the opposite. They're the atoms that want to stay away from each other.
And in the names, there's just Bose and Fermi were two famous physicists who figured out properties of particles, and so they got their name attached to these classifications. There's nothing special about the name.
I heard that Einstein predicted the condensate. What was he working on when he predicted that?
Actually, he was thinking about other things at the time, but he got a letter from an Indian physicist, a guy named Bose.
Very young. Like
A very
18,
young guy,
19.
and in those days, India was not really on the physics map. So he was very bold to write to Albert Einstein. And I've had this idea, I'm thinking about statistics and also trying to explain what's called black body radiation. When things get hot, they glow. And if they get hotter, they glow bluer. When they're colder, they glow redder. And Bose had a way of using statistics, the way the photons mix together to explain this phenomenon of black body radiation. And Einstein always loved statistics. He was kind of a statistical thinker. And when he got that paper, it was in English. And in those days, all the serious papers in science were written in German. So he actually translated the paper into German and sent it off to one of the fancy German journals and said, I think this is a good paper, you should publish. And they said, yes, sir, Professor Einstein, we will. And then meanwhile, Einstein thought about it some more and he wrote a follow-up paper on it, basically just because this Indian guy had got him interested in it.
Mm-hmm. Yeah, and the follow-up paper was about taking those kind of statistics and instead of just applying to particles of light, photons, he applied them to atoms in Einstein's paper, and we, of course, work with atoms. So it was actually a pretty amazing thing that this really senior, famous scientist would, take this letter he got from some obscure kid in India and actually do so much with it.
Regarding the atoms that you did use in your experiment, why did you use rubidium specifically? Why not a different noble gas? What made that the most ideal atom?
Well, it's actually a long history. We sort of started, I was doing completely different experiments working with cesium, and then we started getting into working on laser cooling for cesium because it was just a convenient atom, because it's the transition energy to make the atom go in an excited state and absorb a photon, and then which gives it a little kick. It was just a very convenient wavelength to do that. So we were just, it was kind of an off-the-shelf atom we had and lasers that we had for it. And so we were tinkering around with that for a long time. And then we, ran into we got more serious about going after Bose-Einstein condensation. And then we had other issues that came into play. There were some issues of ease of getting a hold of the right lasers that matched, but then there was a bunch of other physics, and I'll turn it over to Eric to talk about the other physics.
One thing about it is that if you look at the people who've done Bose-Einstein condensation around the world, they almost always use atoms in the alkali column underneath of hydrogen. There's lithium, sodium, potassium, rubidium, cesium, all those, and they all look a little bit like hydrogen. They're all sort of one tightly bound atom, like a noble gas, and an extra electron floating around. So they're particularly simple to work with. Their spectra, the way they absorb light, the color of light they absorb, the patterns aren't very complicated, and the atoms respond very strongly to laser light. And Carl alluded to this, especially not so much for hydrogen, but for the other atoms in that column. Their favorite color, the wavelength of light they really like to absorb, turns out to be a color where the lasers are really cheap. And back then when well, Carl was already a little famous. When I was less famous, I wasn't able to get as much money from the research foundations and so on. And so I wanted to buy cheap lasers. And the lasers to make these kind of atoms glow were the particularly cheap lasers because they're very similar to the lasers which they use in CD players and supermarket scanners and things like that. And so they were sort of like an industrial byproduct from this huge market of industrial lasers. And so the lasers were particularly cheap, which makes a big difference when you're trying to get an experiment running.
The irony to this was that we switched over to rubidium. We had been doing cesium. We switched over to rubidium because of the easy to get lasers and cheaper and so on. And it turns out that there's kind of a pathology of cesium that, and though as we were looking at it, it seemed like, well, all these atoms are ought to do about the same, but cesium has this funny property that it really doesn't like to do Bose-Einstein condensation. So just going after trying to save a little money actually got us the physics we couldn't have done otherwise.
We got a little lucky.
Yeah.
That's not an unusual story in physics or science in general.
How did you account for intermolecular attractive forces between different atoms of rubidium during experiments?
Well, that's a place where, I mean, they're really important and there was an awful lot not known about them, but this was a place where we really had an edge over the other people who after we started pushing in this direction, a lot of people jumped into this race to try to make Bose-Einstein condensation. But we, from the very beginning, realized that you really had to pay attention to these intermolecular forces. In particular, they're very different in their behavior when you get down to these super low temperatures. The atoms behave much more like waves and things at very long distances matter because everything's so cold and slow. And so we had been studying those, and so we did a whole series of experiments probing what those were like, trying to make sense of them, and understanding what exactly the conditions we had to reach because of those. So you want to talk about those?
It helps that we kept the density very low. The atoms were far apart from each other, and as long as there's only two atoms colliding, the attraction forces aren't so important because what they do is they roll towards each other, and it's kind of like two planets attracting each other. They go faster and faster, and they actually hit each other, and they bounce off, but they have
planets don't bounce off. Atoms are a little different that way.
Okay. They bounce off and they come right back out again. They can't, planets would like turn into a molten ball of slag or something, but the atoms bounce off and they come back out, and by the time they come back out, they're going slowly again. So the dangerous thing is if you have more than two atoms, like three atoms, and then right when two atoms kind of bing, that one flies away and these two are stuck together. And then atoms pair by pair stick together and fall out of the trap. So as long as you keep the density, the number of atoms per cubic centimeter kind of low, you can keep what we call three-body recombination small. And you can usually live with those attractive forces. It comes at a price. If you want to go to very low density, to get the Bose-Einstein condensation, what you really want is low temperature, high density. So we're giving up on high density. That means we have to double down on the low temperature, which is why we had to go to temperatures far lower than had ever been seen before in order to make the condensate.
And this idea that it was really important to go to really low densities and therefore really low temperatures, that was kind of one of the important ideas we brought to the business. And so there's a famous early paper we wrote on, I think the low road to BEC.
Taking the low road to BEC.
Taking the low road to BEC, where that was kind of a different direction and turned out to be the right way to get there.
My next question regards how many atoms you would use in each experiment and how you would isolate those atoms.
Surprisingly, not very many atoms. We would start with just a few million atoms, and that might sound like a lot of atoms, but if you ask a chemist, well, what does a few million atoms weigh? And he would say, well, a femtogram or something like that. So it's a tiny, tiny, tiny sample of atoms. But because they're individual atoms, they fill up a fair amount of space, maybe a cubic millimeter or something like that, a millimeter on a side. And we isolated them. We had to keep them from from touching the walls of the box we were holding them in, because the methods we were using for cooling would cool the atoms, but everything else was warm. We could keep them in these glass boxes, and the walls of the glass were room temperature, 300 Kelvin, as we say in physics or chemistry. So we need to keep the atoms from touching the walls of the chamber, but we can't really grab them with anything. Anything we would hold them would get them hot. So we keep them in little magnetic bowls, sort of like it's a little science fiction-y. It's like a bowl of force field, and the atoms roll around in this bowl. The individual atoms they're like little bar magnets which would stick onto your refrigerator. They got a north pole and a south pole, and we applied big coils with currents of wire in it which would generate magnetic fields and push the atoms around. We push all the atoms into the center, away from the glass walls of the box, effectively in this little bowl. In order to get to Bose-Einstein condensation, we had to throw away a lot of the atoms, and our first condensates were really tiny. They had 5,000 atoms, something like that in them, 4,000 atoms. These days we can make condensates which have millions of atoms in it, which are still not very many atoms. You wouldn't, if they all fell in your hand, you wouldn't say, well, God, that's a chunk of atoms.
Yeah.
You wouldn't say, well, my hand feels cold. It's not enough energy there to cool off your hand or anything, really.
I remember some early days when we had this thing, people got attention. We, figured out a new way to cool things with this laser cooling. And I got a call from some executive of a frozen food company, and he wanted to know, gee, is this a better way to refrigerate? And I had to explain to him, no, the amount of energy and cost of, freezing a frozen pea with our approach would probably bankrupt the whole world. So it wasn't going to work for frozen vegetables.
I was also wondering, is it known whether the condensate naturally forms anywhere in the universe?
There are a couple places that they're not exactly the condensate that Carl and I worked with, but related. So we talk about needing a combination of cold and high density, and we sort of went the low road. We had extremely low density gases and extraordinarily low temperatures. You could go the high road to like super, super, super high density stuff, and then you could afford to be a lot hotter, sort of hot kind of temperatures you would find in ordinary matter. And where are things the most dense? They're dense in neutron stars. So actually there's some speculation, which hasn't been proved, that the neutrons in neutron stars get so cold that they pair up.
So dense.
So dense. They're so dense. They're actually not that cold. They're pretty hot. They glow. I mean, they glow. They glow white hot. Even though they're hot, they're that much more dense that they might form a variety of Bose-Einstein condensate called a BCS superfluid. But never mind that. But it's very much like a Bose-Einstein condensate.
But if you're looking at the Bose-Einstein condensate of atoms like we do, it's clear it can't ever happen in nature because we know the coldest place occurs in nature, and that's 3 degrees above absolute zero, and that's because of the energy left over from the Big Bang, the creation of the universe. It's floating around out there. So these atoms are floating around at 3 degrees above absolute zero, and you look at what temperatures we have to get them below 1/1,000,000th of a degree above absolute zero to form. And so that's, any place in nature is 1,000,000 times too hot for this to happen anywhere. So it's kind of fun to be able to say we're sure that it didn't happen anyplace else in the universe unless there's another lab on some other planet there.
The little green scientists out there in the other planet. The Alien Space Foundation funded their
So I was wondering how you managed to trick the atoms into going into the forbidden zone.
into the forbidden zone.
These are bosons. They like to get together. We don't have to trick them. We just have to give them the opportunity, and they jump at the chance.
But it is the case that atoms at this temperature really shouldn't be a gas. They should be a solid. And so Maybe in your high school chemistry class, you made a supersaturated solution, like you made salt water and you cooled it down to the point where it really wanted to be crystals of salt, but the salt couldn't find, it took a long time for the salt to find each other and crystallize. There's also something called, okay, in chemistry they talk about supersaturation. In physics they talk about metastability, which is kind of like that. Basically you can take a gas and cool it down to a point where it really wants to form a droplet of liquid or ice crystal, but it's called the kinetics take a long time. So for instance, oftentimes the water vapor in the atmosphere is supersaturated, but it's only when an airplane goes by and like seeds it that it forms little clusters, and you see the contrail behind that's basically the airplane is taking the supersaturated gas and disturbing it enough that little droplets form. Our job is not to disturb the gas, to keep it very low density, not let it touch anything. And if we do that, we can go into this forbidden zone, get much colder than we're really allowed to. If we happen to have like a little solid piece of rubidium and we put it in there where the condensate was, all the other atoms would stick to it instantly, and then you just have a rubidium ice cube, which is boring. You go to a chemical company, they sell you solid rubidium. So that would be not very exciting. And so you can't let there be that first salt crystal to nucleate the freezing or the liquefaction, and that's the secret.
And that's in the process we were talking about before, where you have to have 3 atoms close together. So if you never have 3 atoms close together, you only 2 atoms, and that means it's just very, very low density. Then that's really what tricks them to not.
3 atoms colliding is the first step on the road to forming crystals or liquids. We keep that from happening, and we can go. But you can do this sort of forbidden thing, which is make this condensate, but you can't get away with it forever. Eventually, no matter where you are, the gas eventually sort of goes away, and what's really happening is it's forming these molecules, these little snowflakes, if you like. And that's
so
that.
A second's a good long time for a condensate to sit around, but you can't trick it forever. It finally figures out it's supposed to be more like a little ice cube. But we can do a lot of physics experiments in a second.
My final question has to do with the commercialization of kind of your discovery. I know there's a startup in Boulder that has looked into commercially producing BEC.
Yes.
And I was wondering if you could elaborate on that and kind of what that would be used for.
So there's a company in Boulder that sells BEC making machines. They don't sell thousands of them, but you can buy a more or less off-the-shelf, turn the key, get your condensate machine now. There are various different commercial uses. One is that cold atoms in general and condensates in particular can be used for sensing very small accelerations, very small rotations. And so there's a group of people who are trying to use them to make the world's best gyroscopes or accelerometers. So, or things for measuring gravity, which is, after all, just sort of acceleration, isn't it? So you could, if you can measure gravity very well or small changes in gravity very well, you can sense things which are hidden underground, like oil or tunnels or these kind of things. So there's a market for that. But maybe the more glamorous thing is, I don't know if you've heard of quantum computers, but quantum computers are the newest, greatest idea for making computers which are much more powerful than current computers. They need to be very cold. A Bose-Einstein condensate is not a quantum computer, but it's very cold. And so in the end, what Bose-Einstein condensate might be is a sort of freon, a sort of cooling liquid for you to immerse your quantum computer in, have it sitting in this Bose-Einstein condensate and being kept cold that way. And there's a lot of work done in that area. So far, not commercial work, research-based work, but it's pretty promising. And I would say around the world, there's hundreds, if not thousands, of people working on that.
Ultimately, for wide-scale commercial applications, you really need a lot cheaper and simpler way to make condensates and make a lot more of it than we do. And I was just thinking about this. It's been just 20 years now, almost to the day, since the first BEC was made. And it's kind of remarkable, given the way science usually progresses, that essentially they're still doing the same way that we started 20 years ago. So it's kind of surprising that nobody's figured out a lot better way to do that yet.